Good morning to everybody. Myself, Dr. KARTHICKEYAN, Professor from EEE Department, Amet to be University, Chennai. Today, we are going to discuss about inverters, types and its control. So, in this lecture, we are going to discuss about introduction about the inverters, then classification of inverters, then single phase voltage source inverter, and then three phase voltage source inverter. Then we will discuss about the voltage control techniques of inverters, and finally we will discuss about the PWM techniques which are used for a voltage control of inverters. Okay. First, what is inverter? Inverter is a static device which is used to convert a DC input into AC output of desired voltage and frequency. And the application of the inverters includes variable speed drives which are widely used in industries, and induction heating, and then standby power supplies, and finally we can use it for UPS, uninterrupted power supplies, and we have many industrial applications like this. Then classification of inverter. These inverters are basically have two types. One is single phase inverter, another one is three phase inverter. And also these inverters are using a power switches which are the fully controlled devices. These devices are maybe the BJT or MOSFET or IGBT. So the classification is also based on the different method of commutations used in these power switches. First one is based on this method of commutation. We have two types. One is line commutated inverter, another one is forced commutated inverter. In case of line commutated inverter, we don't have any external circuit or any additional component for commutation. So the circuit itself it will automatically turn off and ready for the next cycle. But in the case of forced commutated inverters, we need some external circuit to turn off the circuit. So these are two type of inverters based on the commutation. Then next one is according to the method of connection. We have three type of connections. One is series inverter. In this inverter, the power switch as well as the load are connected in series. That's why it is called series inverter. Then parallel inverter. In parallel inverter, the power switches and the load are connected in parallel. So final one is bridge type inverters. In this bridge type inverter are most widely used in nowadays, and in this inverter the power switches are connected in bridge circuit. And finally based on the type of DC sources used in inverter, we have two types. One is voltage source inverter, another one current source inverter. In this lecture we are going to discuss about this voltage source inverter. Now we will discuss what is voltage source inverter and what is current source inverter. Voltage source inverter is an inverter which uses a constant DC voltage source as a input. In this voltage source inverter, the output voltage does not depend upon the load, whereas the output current depends on the load. That is called voltage source inverter. Then current source inverter. In the current source inverter, we can use a constant DC current as a input, and in this the output current does not depend on the load, whereas the output voltage depend on the load. Now we will discuss about the various type of voltage source inverter. First we will discuss about single phase voltage source inverter, then three phase voltage source inverter. In this single phase voltage source inverter, we have two types, that is off bridge inverter as well as full bridge inverters. Similarly, in three phase voltage source inverter, we have two types. One is 180 degree mode of operation, another one is 120 degree mode of operation. First we will discuss about a single phase off bridge inverter. In this single phase off bridge inverter, we have two DC sources, Vs by 2 and Vs by 2, and similarly we have two main switches, that is power switches S1 and S2. As I already told you, these power switches may be the BJT or MOSFET or IGBT. And we have two diodes which are connected anti-parallel with the power switches. These diodes are called feedback diodes. These diodes are very useful when you are using a R load here. But for simplicity here I have considered only a simple R load. The load is connected across the midpoint of the voltage source as well as the two main switches. Now we will discuss the operation of this single phase half bridge inverter. This operation can be divided into two modes. The first mode, consider that the switch S1 is closed and switch S2 is open. When the switch S1 is closed, the top source Vs by 2 will supply the power to the load through the switch S1. So here I have assumed that polarity of the load like this. So that whatever the voltage available during this first mode is positive, and same way the current is also considered as a positive. And during this mode, the switch S1 is responsible for the entire load current. So the entire load current will be flowing through the switch S1. So this is current through the S1, and the current through S2 is 0. This is your load current. And during the mode 2, I am going to turn off the switch S1 and turn on the switch S2, so that the mode 2 starts. During this mode, the bottom source Ps by 2 will supply the required power to the load. During this operation, the direction of voltage and current are reversed. That is why we are getting a negative output. Here we are getting a negative voltage output, load voltage. During this mode, switch S1 is open, so there is no current through the S1, and the entire load current will flow through the switch S2. So the current is reversed. So we are getting a positive half cycle as well as negative half cycle. During mode 1, we will get the positive half cycle. During mode 2, we will get the negative half cycle. This will be repeated for the next cycles. So this is the operation of simple single phase half bridge inverter with R load. If you are using a RL load, due to the energy stored in the inductor circuit, the energy will be fed back to the source through this feedback diode. This is the purpose of having a feedback diodes here. But there is no function during the we are using a R load. Next we will see about the single phase full bridge inverter. Here in single phase, in case of single phase half bridge inverter, we require a center tapped power supply, input supply. But whereas here we require a single power supply. Here we are using a 4 switches S1, S2, S3 and S4. All the 4 switches having an anti-parallel diode, which is called feedback diodes. And the load is connected in between the midpoint of the switches and both leg of the switches. Okay. Now here I consider a positive on the left hand side and negative on the right hand side of the load. Therefore, when the current is flowing on this way, we have considered as a positive cycle. If it is a reversed, it is a negative cycle. So the operation of this single phase full bridge inverter, again it is divided into two modes. During the first mode, I have turned on the switch S1 and S2. I am applying a gate voltage or to the S1 and S2. So I am getting a positive output voltage. So during this mode 1, S1 and S2 are conducting. The current is flowing in this way. The polarity of the output voltage is positive, and the same way current is also positive. So I am getting a positive output voltage. And during negative half cycle, I turned off the switch S1 and S2 and turned on the switch S3 and S4. Therefore, the current will flow from the source S3 load and S4 finally it will return back to the source. So now the polarity, if you see the polarity of the current, it is reversed. That is why I am getting a negative half cycle. So I am getting a negative output voltage here. So this will be repeated for the next cycles. So in this way I am getting a AC output voltage from the available DC source. So this will give you the single operation of the single phase full bridge inverter with R load. So next we will discuss about a 3-phase voltage source inverter. First, we will discuss about a 180-degree mode of operation. Here, we have 6 switches T1, T3, T5. That is odd number switches are the switches available in the upper leg is are odd number, whereas the switches in the lower leg are numbered with the even numbers. So it will be easier for remembrance. Here we have a single source. All the sources are all the switches are connected to this single source through these 2 capacitors. This is for nothing but for voltage balancing. Here I have connected a simple R connected star load, 3-phase R load. Here the operation of this 180-degree mode will have 6 modes of operation. Each mode will exist for 60 degree, and for each at any mode of operation or at any time of operation, there are 3 switches conducting. So the switches conducting at any time there are 3 switches are conducting. Out of these 3 switches, either 2 from upper side, 1 from lower side, or otherwise 1 from upper side, 2 from the lower side. So that the operation will be achieved. So these are the various modes of operation. During mode 1, the switches 5, 6, 1 will be conducting. Here the 5 and 1 are the upper side switches. 6 is a lower leg switch. Similarly, in mode 2, 6, 1, 2 are conducting. Here, the 6 and 2 are the lower side switches, and 1 is the upper side switch. So, in this way, in each and every mode, 3 switches are conducting at any time. First, we will discuss about the mode 1 operation. Here, in mode 1 operation, the switches 5, 6, 1 is conducting. During this mode of operation, the voltage source Vs is applied to all the 6 switches, but only the 5 and 1 are connected or turned on. So these switches are connected to the load. So this is the equivalent circuit diagram for this mode of operation. In this mode, the switch 5, 6, 1 is conducting. Here 2 upper switches are conducting and 1 lower switch is conducting. During this mode of operation, the output is voltage, that is VRN is the phase voltage, that is Vs by 3. Then Vyn is the minus 2 Vs by 3, and Vbn is the Vs by 3. Here we have VRN and Vbn are positive voltages, and Vyn is the negative voltage. This Vyn is belonging to the lower leg. So we are taking a minus symbol here. So these 2 are the upper leg, so we are getting a positive signal. Here, wherever we have 2 switches are conducting, that side we have Vs by 3 voltage, and another side we will have 2 Vs by 3 voltage. Okay. So the line voltages are Vry is equal to Vs, Vyb equal to minus Vs, Vbr equal to 0. If you add all the 3 phase voltages, you will be getting 0. Similarly, when you add all the 3 line voltages, you will be getting 0 at any time. Similarly, for mode 2, the switches 6, 1, 2 are conducting. Here, 1 switch from upper side, 2 switches from lower side. Now we will see the equivalent diagram for this. So this is the equivalent diagram for this mode 2 operation. In this, 1 switch is conducting in the upper side, 2 switches are conducting in lower side. So this lower side will have Vs by 3 voltage, and upper side will have 2 Vs by 3 voltage. The polarity of this 2 Vs by 3 is positive because it belongs to the upper leg, whereas this Vs by 3 belongs to lower leg, so it is having a magnitude of minus Vs by 3. So these are the phase voltages Vrn, Vyn and Vbn, and the line voltages are going to be Vry is Vs, Vyb is 0, Vbr equal to minus Vs. So in this way we can draw different modes of operation for all the 6 modes, and the waveform of this will be we arrive at different phase voltages and line voltages like this. for waveform of this is going to be, these are the phase voltages, three phase voltages for this 180 degree mode of operation. Here VRN, initially it is Vs by 3, then 2 Vs by 3, then Vs by 3, then 0, then again Vs by 3, again 2 Vs by 3. Likewise, it will be a stepped waveform. The VRN, VYN, VBN are the stepped waveform in case of 180 degree mode. That is, phase voltages are stepped waveform. Then line voltages VRY, VYB and VBR. If you see these voltages, it is either Vs or minus Vs, or it may be 0. So it is a quasi square waveform. These line voltages of 180 degree mode of operation are quasi square waveform. Next, 120 degree mode of operation. Again, the circuit diagram of the 180 degree mode of operation and 120 degree mode of operation both are same. There is no difference in the circuit diagram. Only the thing is operation is slightly varied. Here, for 120 degree mode of operation also we have 6 modes of operation. Each mode will operate for 60 degree, and only the difference is at any point of time only 2 switches will conduct, and these 2 switches, one is from upper leg, another one is from lower leg. So the switching devices are, during mode 1 6 and 1 will conduct, during mode 2 1 and 2 will conduct, during mode 3 2 and 3 will conduct, during mode 4 3 and 4 will conduct, and 5 4 5 will conduct, 6 5 6 will conduct. Again this cycle will be repeated. So now we will see the waveforms or modes of operation. First consider a mode 1. During mode 1 the switch 6 and 1 is conducting, 6 is from lower side, 1 is from upper side. The equivalent circuit diagram for this is going to be like this. So whatever the voltage applied here, that is Vs, the input voltage Vs is available across both the phases. So it is equally divided. So it is Vs by 2, and if you see the phase voltages VRN, it is going to be Vs by 2, then VYN equal to minus Vs by 2. So these are all the phase voltages. Then line voltages VRY equal to Vs, VYB equal to minus Vs by 2, then VBR equal to minus Vs by 2. Again, if you add all the phase voltages or any line voltages at any instant, it is going to be 0. Then mode 2. Mode 2, the switches 1 and 2 are conducting. For this mode of operation, this is the equivalent circuit, and the various phase and line voltages are going to be like this. That is VRN equal to Vs by 2, VYN equal to 0. There is no device conducting during this Y phase, so the VYN is going to be 0. Then VBN equal to minus Vs by 2, because the lower side switch is conducting. That's why we are getting a negative symbol here. Then the line voltages VRY equal to Vs by 2, VYB equal to Vs by 2, and VBR equal to minus Vs. So these are the various phase and line voltages applied for different mode of operation. Based on this, we can draw the waveforms. So these are all the phase voltages for 120 degree mode of operation. During this 120 degree mode of operation, you will be getting a quasi square waveform output for phase voltages. Whereas line voltages, again it is going to be a stepped waveform. So this is the difference between 180 degree mode of operation and 120 degree mode of operation. So the major difference is, during 180 degree mode of operation, 3 devices will conduct at a time, 2 from upper side, 1 from lower side, or otherwise 1 from upper side, 2 from lower side. Whereas in the 120 degree mode of operation, we have only 2 devices conduct at any time, and these devices, 1 from upper side, another one from lower side. And the output waveform of the 180 degree mode of operation, the phase voltages are going to be stepped waveform, line voltages are going to be a quasi square waveform. But in case of 120-degree mode, the phase voltage is going to be a quasi-square waveform and the line voltages are going to be a stepped waveform. These are the difference between 180-degree mode of operation and 120-degree mode of operation. Then coming to the control, the voltage control, we have several type of control. Here in this session we are going to discuss about only the voltage control. The requirement of the load is maybe a constant voltage or variable voltage in the load terminal. So the control is we can control the output of these inverters in different ways. Either we can control the this is going to be our inverter. We are going to give the input as a DC. We are going to get the output as a AC. Whatever may be the input, the output should be based on your load. The output should be suitable for your load. So we are going for a voltage control of different methods. First method is we can control the AC output voltage by externally. That is external control of AC output voltage. The second method is we can control the input DC voltage. Externally we can control this DC input voltage so that we can get the different output voltage. And the third one is going to be the control within the inverter itself. So we are going to integrate the control part within the inverter itself. So this is the most popular one. Most of the inverters we are using this third method only. The first two methods require some additional component to achieve this target, whereas this third method does not require any additional component. So first we will discuss about the external control of AC voltage. To control the AC voltage, we have either we can control the output voltage by using a AC voltage controller. For example, if we are having a constant DC voltage, this will be given to the inverter so that we will get a constant AC output voltage. This constant AC output voltage again given to the AC voltage controller, which can control the output voltage, which is suitable for your load. This is one method. So this method output contains more number of harmonics, and it is that is why it is very rarely used. And then the next method is series inverter control. We have number of inverters connected in parallel. These output of the inverters are connected to the transformers. Number of transformers, and the secondary of all these transformers are connected in series, so that we will finally get the output voltage is the sum of all the secondaries of output voltage. So for example, if you consider two inverters are connected with the two transformers, the secondaries of these two transformers are connected in series, so that we will get the sum of the vector sum of these two output as a final output. That is V0 equal to V01 plus vector sum of V01 and V02. The major thing is here the frequency of these two inverters should be the same. Then only we can use this method. Then next method, we can control the input DC voltage. So if you are having a constant AC voltage, this can be controlled. This can be converted into a DC voltage with a required level by using a fully controlled rectifier. And this is a controlled rectifier, so we can control the output voltage of AC to DC converter. So this controlled DC voltage is applied to the inverter so that we will get the controlled AC output. This is one method. The another method, if we are having a constant AC voltage again, we can use the uncontrolled rectifier also. If we are using an uncontrolled rectifier, again it can be controlled by using an additional chopper here. So uncontrolled DC is converted into controlled DC. This controlled DC is given to the inverter so that we will get the controlled AC voltage. Next one is if we have a constant AC voltage, this can be given to the AC to AC controller, that is which convert the constant AC voltage into variable AC voltage. This variable AC voltage or controlled AC voltage is given to the uncontrolled rectifier This will give you the controlled DC voltage. This controlled DC voltage again inverted by using an inverter, so that we will achieve the controlled AC voltage. The next method is, if you are having a controlled DC voltage, then we can uncontrolled DC voltage, this can be given to the chopper circuit, so that we will get a controlled DC voltage. This controlled DC voltage is converted by the inverter to a controlled AC voltage. Then the next method, which is most popularly used nowadays, inverter control of inverters, that is the internal control of inverters. Here we are using a pulse width modulation technique, which is used to control the width of the output pulses, so that we can achieve the required level of output voltage. This pulse width modulation also controls the frequency of the output. So this pulse width modulation, in addition to the voltage and frequency control, it is also used for harmonic control. So this have many advantages like this. So we are using the internal control of inverter by using a pulse width modulation techniques. So pulse width modulation inverters, the inverters which are using a pulse width modulation as a control technique, that is called pulse width modulated inverter or PWM inverters. So by using this pulse width modulation, we can control the output voltage as well as the frequency. The quality of the output voltage of this PWM inverter are enhanced by this pulse width modulation, because by using this pulse width modulation, the harmonics are very much reduced. So different type of PWM inverters. We have single pulse width modulation PWM inverters, multiple PWM inverters, then sinusoidal PWM inverters, then modified sinusoidal PWM, then space vector PWM. Each and every method it has its own advantages and disadvantages. First we will discuss a single pulse width modulation. In a single pulse width modulation, there is only one pulse exists per half cycle. So the output contains only one cycle per half cycle, only one pulse per half cycle. So the number of pulses in the output is going fixed one, that is 1. So consider this fully controlled rectifier, full bridge converter. So here I have given it 1 and 2 one pulse, and 3 and 4 another pulse. So I am getting a alternating voltage waveform like this, square waveform. So it consists of only one pulse during per one half cycle. So in this, the number of pulses are fixed, that is only one per half cycle. Therefore, the control is very easy. We will see that how we can generate these control pulses by using a carrier waveform as well as a reference waveform. Here the carrier waveform used is like a sawtooth waveform or triangular waveform. Then you are using a constant reference DC voltage. By comparing this reference voltage reference signal as well as the carrier signal, you are achieving the positive off cycle control signal and negative off cycle control signal. This is achieved by comparing the both carrier waveform as well as reference waveform. If the magnitude of reference waveform is greater than the carrier waveform, you will be getting a positive off cycle pulse. Similarly, whenever the magnitude of reference waveform is less than the carrier waveform, the negative off cycle pulse will be generated. By using these pulses, we are able to achieve this quasi square waveform by using this full bridge inverter. So this is the technique used in a single pulse width modulation. In this, the frequency of the reference signal determines the frequency of the output. That means if you are changing the frequency of the reference signal, it will control the frequency of the output. And the magnitude is depends upon the modulation index. Modulation index is nothing but the ratio between the amplitude of reference waveform and amplitude of carrier waveform. Then multiple pulse width modulation. Before going to the multiple pulse width modulation, the major disadvantage of single pulse width modulation. Here in single pulse width modulation, you have only one pulse per half cycle. So the output is going to be a square waveform or quasi square waveform. Because of this quasi square waveform or square waveform, the harmonic content in the output is very high. In order to reduce that, we are going for multiple pulse width modulation. In this multiple pulse width modulation, instead of having a single pulse, we are going to have a number of pulses. So when you increase the number of pulses, the output waveform is also modified. So the harmonic contents will be reduced. So here this multiple pulse width modulation is achieved by using, instead of having a single carrier, we are going to have a multiple carrier here. So these multiple carriers are compared with the reference signal, so that we will achieve the different multiple pulses here. So in this way only we are having. Here you can see I am using a triangular waveform and one rectangular waveform. These two are compared and the multiple pulse per half cycle will be generated. The pulse width of each pulse is going to be equal in this method. So that the frequency of the reference waveform determines the frequency of the output, and that modulation index determines the amplitude. Then sinusoidal pulse width modulation. In the sinusoidal pulse width modulation, instead of having a reference signal as a constant DC voltage, here we are going to use a sinusoidal signal as a reference waveform. So we are using a sinusoidal as a reference. The number of pulses in the output is again going to be a multiple pulses, and the pulse width is going to be varying, depends upon the magnitude of the sinusoidal waveform. Again, the modulation index determines the magnitude. So here I am using a triangular waveform as a carrier signal and sinusoidal waveform as a reference signal. Here the width of each pulse is continuously varying. When you see the pulses, in the middle portion the width of the pulse is going to be higher, whereas in the side bands the width of the pulse is going to be reduced. So because of this, the harmonics and the output voltage is greatly reduced. This is the main advantage of this sinusoidal pulse width modulation. So up to this we have discussed about the classification of inverters, single phase inverter, three phase inverter, voltage source inverters and current source inverter. Out of these, the voltage source inverter is elaborately discussed and various control techniques used in this method are discussed and different PWM techniques are discussed. Thank you.